Cobwebbing is one of the coolest inventions in the calculus stream I've ever seen. It is actually so cool that I would wish I would have invented it myself, but unfortunately I didn't. So cobwebbing allows us to study difference equations, something like this, without doing any math. It is a completely graphical method, and it really allows us to completely understand the dynamics of such a difference equation. So here, for example, I have f of x is square root of x. So then the corresponding difference equation is xt plus 1 is equal to square root of xt. And so then here I give you an example. So if I start with 0.2 and sub it in, then I get the square root of 0.2, which is 0.447. And then I take the value for 0.447 and I sub it in, and I get 0.668. And then 0.668 substituted gives 0.817, and then 0.817 goes to 0.903, etc., etc. So we can do this on the calculator. But how to do it graphically? Well, we have learned one thing already. We know that the intersection of the updating function and the diagonal gives us the equilibrium points. So why don't we start right there? So here I plot the function f of x and the diagonal line y equals x, and where they intersect, which is right here and right here, we have equilibrium points. So these are two equilibrium points at 0 and at 1. But what does the system do in between? So let's try to follow these computations which I did here on the side in the graph. So I'm starting at 0.2, which is right here, and I evaluate the function at 0.2. I'm losing my equation, so this one is the equation. So I need to substitute 0.2 under the square root, and the result is 0.447, or in other words, I go up here to the function, and then the value at the function is 0.447. And now I have to do it again. So I need to kind of graphically transport the value 0.447 to the x-axis. Well, it is somewhere here. But there's a smart way to do this, because we can use a diagonal. So I move this over to the diagonal, somewhere here, and then I go down. And I get exactly the value I want. So this is 0.447. It has to be, because the diagonal says y equals to x. So it can be used to mirror one value from one axis to the other. Okay, so now I have this value, and I sub it into the function again, which means I go to the function. And I get the next value, right here, which then is 0.668. And then I need to mirror image this point down to the x-axis for the next iteration. So then here is, what is here, 0.668. So then I go to the function again to get the next value, which is 0.817. And I mirror this on the diagonal to get the value on the x-axis, 0.817. And I do it one more time and get the next point and go to the diagonal and go to the function and go to the diagonal. So I get kind of a step ladder picture of the points of my iteration. And I could have done this without knowing the numbers, right? I could just do it without knowing the numbers. Let's see in the next example. So here we have another example, which is a Hill function, which are commonly used in biology. f of x equals 2.4x squared divided by 1 plus x squared, and the function is shown here as a graph. And I've shown the diagonal, y equals x, and let's play the game again. So I start, maybe this time I start at 0.4. So the rule is you go to the function, then you go to the diagonal, then you go to the function, to the diagonal, to the function, to the diagonal, to the function, to the diagonal. This is cool, isn't it? So I know I start at 0.4. The next value is about here, which is a little bit more than 0.3. The next value is a bit more than 0.2. The next value is about 0.1. So I can see what my iteration does, and it looks like actually it converges to 0. So let's start here maybe at 0.7. I go to the function, I go to the diagonal, I go to the function, to the diagonal, to the function, etc. And so then I get the iteration here, and this seems to continue growing even beyond 1. So this is called cobwebbing. Cobwebbing. Now, in these examples, it didn't really look like a cobweb. But if you have more complicated functions, it does start to look like a cobweb. So here I have two more. So these ones are more oscillatory, and then let's see what happens if I start my iteration, let's say at 0.1. I go to the function, I go to the diagonal, which means I kind of mirror image the value down here. I go to the function again, I go to the diagonal, and for the next iterate the function, the diagonal, etc. And see what I get here is, it seems like I'm oscillating around this point, and in the middle there is a fixed point, or an equilibrium. So I'm kind of oscillating around the fixed point. How about here? So here maybe I start in the middle somewhere, and then the iteration or the cobwebbing gets me around and around and around and around. And so this is magic. You have to do this. Plot out maybe the PDF file of these video notes, print them out, and then do it yourself. This is just so cool. So it seems like here we are oscillating towards the fixed point, and here we are oscillating out and going away. So maybe draw some arrows. So first we started here, and then we come down here, and we go up here, and we come down here, and we go up here, and we come down here, and we go up here. This is called cobwebbing. And see, at these two curves I didn't do any math. I didn't do any computation at all. It is purely graphical, and that's why it's so cool. So there's another way to show the solution which relates more to what we have learned before. And so what we have learned before is that in a recursive relation or a difference equation, we write down the iterates, 1, 2, 3, 4, 5, 6, 7, etc. Right, and then we would have a sequence of points which do whatever they do and maybe converge to a point. So now the question is, how do we get this sequence of points from our cobwebbing diagram? And this is equally cool as everything else before. Let's start with 0.1. So 0.1 is the initial condition, and I just draw it until the diagonal, and then I take this value all the way over to the other graph, and this would be my initial condition at time equal to 0. And then I do my first iteration, just change color. I go to the function, and then from the function to the diagonal, and then again I transport this value over to my iteration t is equal to 1. And so let's call this axis xt for the iterations. And then I do this again. I go to the function for the next iteration, and I carry this to the diagonal, and then I carry it over to the point number 2. So this would be my second iterate. And let's do one more. I go to the function, to the diagonal, and then this value is taken over to the point number 3 right here. And this way you can project the cobwebbing diagram into a time diagram where, as a function of time, you see all the points, how they arise as the iteration progresses. It's a cool method. So this cobwebbing is actually quite popular, and there are a few online resources which I'd like to show you. Let me summarize. So cobwebbing is one of my most favorite tools to analyze first-order recurrence relations, or as we call them, difference equations. You would be expected to draw a cobwebbing diagram for a simple function. So if I tell you, for example, plot sine x between 0 and 2 pi and do a cobwebbing diagram, you should be able to do that. Or if I give you the exponential function and ask you to do a cobweb diagram. As I say, try it out, plot a few functions, just do it on a piece of paper. It is absolutely fun to do. Help me! Help me! To the rescue! Who is gonna help me? Oh my goodness! Please help! And there he comes, Cobweb Man, to the rescue!